Recording started, yeah.
Yeah,
Okay.
yep.
It's already started.
Okay, so here it's about, let's share the screen. I'm going to share the one to the left, that one. And here is the presentation I wanted to go through. I have to, just a moment. Here it is. And let me see if it works in full screen mode. Sometimes it doesn't. Can you see that? Oh, now you see the presentation mode, huh? Yeah, I'll go this way.
Yeah.
So for the for Modtran itself, first thing is what to use it for, Modtran. And I think that's what you want to do is sensor definition. So if you want to have a new sensor. Second thing is if you want to calibrate and validate your sensor, so to see if it really measures what it should. And the third thing is to do some cross analysis, so compare it to other measurements and so on. That's a typical use case of Modtran. And in your case, you said you wanted to simulate at sensor radiances in various situations. So is this for design of a new sensor, or is it for better understanding what's happening, or what's the goal behind?
The goal behind is to be able to detect methane emissions from various locations, actually.
Yeah. So to simulate, to develop methods for the analysis of Sentinel data.
Yeah.
Mainly. Yep. So you want to better understand the Sentinel, what it's measuring. Yep.
Yep, pretty much.
Yeah. And for the radiance components, that's always popping up. You said you're interested in the at sensor radiance. That's the total LFs, and you have to be aware that it's an addition of various components in the radiance. And specifically, last time you mentioned water applications as well. So in water, very little of a portion is coming from the ground or from the water, and a lot is coming from the surroundings in certain cases. So one has to be really aware if you do at sensor radiances for dark objects. What you see is not your ground signal, but mostly your atmospheric signal. So you have this path scattered radiance, which is coming directly from the atmosphere, and the adjacency radiance from the surroundings, which are the additional parts coming in. I think there is one person waiting. Yeah, I have to admit her. So now that's just the first. So what you have to input for the calculation is always more or less the same. You got to know the geometry of the situation. So this is given by the location, or by if you know it directly, by the angles of the observation. So with Sentinel, usually you're looking downwards, but the Sentinel has quite a big field of view, so you look also to the sides. So you have to be aware if you look sidewards, or if it's really nadir, so what is the sensor observation angle. Then you need as a geometry of the sun. So this means the location of the sun, and you need the day of the year for the Earth-Sun distance. So this is all geometric parameters. In Modtran, there are various options how to enter it. Either you enter directly the angles, or you enter location and time or day of the year, and then it will be calculated elsewhere. So that's how you can enter the geometry. Also in the geometry is the height, so height of the ground, height of the sensor. For satellites, that's something I mentioned last time. It's always 100 kilometer is the sensor altitude, and the ground, of course, is somewhere whatever you have on the ground. This is also given in kilometers normally. Then for the atmosphere in between, you have to give the composition. This is given by the standard atmosphere, like for the gases, the aerosols. It's also is the pressure and the temperature, but for Sentinel, these two parameters, last two are not relevant. So you don't have to care if the temperature is different. Temperature plays a role if you work in the infrared, but not in the visible near infrared. And pressure also has not a big impact. The third is the source of the sun. So this means what solar spectrum you're using in the background. Here again, for broadband data like Sentinel, you don't have to care a lot about that. And then you need the wavelength range and resolution. So you need the sensor response functions. That's something you received already to know which range to simulate. And last but not least, you have to be aware what target you're looking at. So in your case, the question is, which targets are your most interest? I heard last time it's in some cases it's water. Is it what is your target of interest?
Our main target is to detect methane CH4 and to remove any other constituents that might be detected by Sentinel.
Mhm.
Because let's say Sentinel captures methane, right? It is in one of the bands that Sentinel can capture, but it can also capture water and CO2. We want to remove any other tracer gases so that we can only focus on methane alone.
But how did you get to use Sentinel with the trace gases? Because this is quite difficult. So you need a lot. It might be possible if you have really a strong signature, so a lot of CH4. But with Sentinel, it will because it's not a spectrometer. You don't see the spectral feature there. So I'm not sure if this is feasible. One can try, but yeah.
Yeah.
Anyhow.
Currently we are trying it out for the large plumes based on research done by others and as well. But yeah, we are trying to actually remove all the other constituents as well, because Sentinel, as you said, it's not feasible, right? But we are trying it out.
Okay. So this is for the inputs. The outputs you have is normally the sensor radiance. That's what you want, but also the transmittance can be output or the ground irradiance. So what you have on the ground. And as a side outputs, you get the complete atmospheric profile, the columns of the gases, and the optical thickness. This is just the outputs here. So there's a bunch of outputs from Modtran, not only at sensor radiance, but also the information about at sensor radiance is stored every time you run it. And now for the what are the assumptions in Modtran? So it's a forward simulation. This means Modtran starts at the top of atmosphere and goes step by step through the atmosphere to simulate what's happening to the radiance. So it goes through the layers, layer by layer, does the scattering at the layer, and it's about 30 layers of the atmosphere it's going through, going to the ground and then up again. So this is the principle. This means it's not invertible, so you cannot go the other way around. You cannot say I know the sensor radiance and then I want to know what's on the ground. It doesn't do atmospheric correction by default. So Modtran is really for forward simulation. That's what we call forward. For inversion, you'd need an atmospheric correction package like AdCore or the others. And yeah. Now, other assumptions are that you have standard profiles. We talked about this last time. We looked into the profiles already a little. And you assume that gases and the aerosols decrease exponentially with height. So this means you don't have inversion layers of things like that normally. For the surfaces, we assume that it's inversion. And polarization is not included. This is relevant for aerosols, so it's not sensitive to polarization. That's the current the assumptions behind. The Modtran 7 should be sensitive to polarization, but it's still quite a path to go to until it might be released. So apparently the development of Modtran has stuck in the meantime, and the Modtran 6 is there to stay for a while, the current release. And it's a very ripe product, a very ripe program. This is about the radiative transfer codes you got. You have Modtran. Did you work with 6S as well?
Yeah, we have worked with 6S before, but we couldn't really produce much results.
Mm-hmm. Yeah, it has less options, and Modtran is more complete. Yeah, and there is also Libratran, which can be used, which we are starting to use. The advantage is it's really available, and you can do almost everything you can do with Modtran, but it doesn't have any user interface, so you have to dig into the code to run it. There are others like Matisse and so on, the French developments. And the term Hytran often pops up. So Hytran is not a radiative transfer code. That's the database of all the molecules and what's happened. So it's a storage of all absorption coefficients. And Modtran uses the Hytran database in the background. So this, you had to, for the installation, you had to download these high resolution databases of the gases. And this was the Hytran database in the background, which is downloaded. So this is about the overview of the codes. There is also some more information here to compare each against each other. Modtran has also the difference that it's working in the infrared as well, so in the thermal infrared. Big disadvantage is that it costs, so that's why more and more people are using different codes in the meantime. But as I said, it's well established, and if you do publications, people like nobody will complain if you use Modtran. So that's the advantage of it. The development is done by Lex Berg. Well, he's the one really knowing everything about Modtran. So if you have a fundamental question, you would need to approach him and Spectral. So that's Spectral Sciences in the USA who are doing the development. On the other hand, Lex is also getting older, so he's also approaching the 70 years. So that's why maybe the development is not that fast anymore. And I'm not sure if it's taken over, what the future plans are, but that's just the current situation. And the main developments they're doing at Spectral is for the U.S. Army, and they're also getting the main money from the U.S. Army. So their focus is maybe in different things currently than it was before. So the civil part is not their main focus. Questions about these codes? Sorry?
Can you repeat it?
Are there any questions?
Oh, no. None so far.
Now for the Modtran and Modo integration. So as you know, Modo is only a GUI for Modtran and a wrapper. So it doesn't do the processing itself. So whenever you run Modo, it writes these input JSON files. These are the steering files or ASCII files. And there you also may store the spectral albedo. So this is ground data, ground reflectance. And then you run Modtran based on these two files. So whenever you do anything in Modo, first a JSON is written and then Modtran is called normally. And so this also means you could use the same JSON files to run Modtran directly from the prompt, because Modtran itself is a binary which can be called without Modo in the command line. And then the outputs are these so-called tapes. So it's tape 6 and tape 7. Tape 6 is not mentioned here. Tape 7 contains the main data. And tape 6 contains also the side information. So if there was an error or if something goes wrong, you should consult tape 6 as well, and not only tape 7. In tape 6, there is some text and some information, what's going on or what went wrong. if something is not working as expected. Another side output is the solar flux. So flux means the irradiance on the ground. So if you want to know what's happening on the ground, you need to analyze these files. These are all ASCII files in Modo. We always configure it as ASCII. You could output as binary, but we just go the easy path. And Modo then evaluates this data. It uses maybe a sensor response to create the radiance at sensor radiance. And finally, does a convolution. This means it transforms it to the response of your sensor. So that's done in Modo again. So we just run Modtran inside in standard configurations without any sensor. Only the limits are given, and then the evaluation and the input preparation is what Modo does. That's for the setup. And for the GUI, you have already started it. I think I don't have to go for it. It's based on IDL, so you need the ideal virtual machine in the background. This is distributed in the RISI software. If you got a NV license, you could also use that ideal virtual machine, but that's just a requirement in the background. Formally, the old inputs were called tape 5. Maybe from time to time you will see those. They were ASCII files like this, very hard to read. And very strictly formatted ASCII files. I think we don't use them anymore, but maybe if you got some old data, you may need to transform that to this new JSON file formats. So you have seen this JSON input files which are just all parameters written one after the other. The information of the parameters can be found in the Modtran manual. So the Modtran manual contains the description of all these parameters of the JSON file. And there are a lot. So usually you have to, you got to know what to change. So usually one starts with a default JSON file, and one only changes what has to be different than the normal. So don't write it from scratch. That's too complicated. So use a template, and then from this template, one changes the most important parts. This JSON file translates to this big GUI you have seen before. So that's this one. And this is just a translation line by line. So if you see the JSON, this first group here in the JSON file is the first line in the GUI. This corresponds to this first line here. Or the second portion, the atmosphere, corresponds to the second block in here. So that's how it's organized. So it's not necessarily logical, but it's in a way that you can find the respective parameter in the JSON file directly in this huge GUI here. So that's was the idea of this GUI. It was not to have a nice human interface. It was having a translation of the JSON file. And the most important parameters are in here, not all of them. So some of them have been omitted because Modo has been written for remote sensing. So this means certain parameters are seldom used in remote sensing, and that's why they were left out in this GUI. But that's just the main the GUI. There are smaller GUIs later. Something about the definitions. There is the solar zenith angle, which is the angle which is 0 if looking upwards, and it's the deviation from the perpendicular to the ground. So this is the solar zenith. Then the sensor zenith angle is also from upwards looking, it's 0. If you look downwards, it's 180 degrees. And if the sun is always somewhere between 0 and 90 degrees, obviously, and the sensor is usually between 90 and 180 degrees. Then you got the side sun angle. This means that's the angle between the observation vector and the solar vector. This, if you look downwards directly nadir, then this angle is not relevant. Then you have the two heights, the height of the sensor, the height of the ground. It's called H1, H2. H1 is the sensor and H2 is the ground. That's the conventions, how you use it. And then for the input of the spectral albedo, so the ground reflectance, that's a synonym, spectral albedo and ground reflectance in Modtran. Scientifically, spectral albedo means it's fully Lambertian, doesn't have a dependency on the angle. So it would be the so-called prehemispherical reflectance, BHR, or white sky albedo. It's also synonym to that. That's what Modtran uses. It doesn't do BRDF things on the ground. That's how you import it, but you could also import a spectral library if you have some ground spectra somewhere and use those, but you have to import them to Modo to store it in the so-called specalb format called specalb.dat. This is a default which is already given by Modtran, but you could replace it or use a different one for the ground reflectance. That's for CH4, it's maybe not that relevant. Here is what we already started last time, this at sensor radiance simulation. So that's an east down. This is the complicated interface. This is already a little bit easier. So you have the most important parameters only, and you select the sensor response, and then you can create at sensor radiances for a standard situation only. This does not include changed situations. Now here, that's how the modeling approach is. You usually start with a standard configuration, and you change certain things like the atmosphere or the sensor response or the geometry or the surface reflectance, and then you run it with Modtran. After you have to extract the spectra and do the convolution to your sensor. So that's just how the process works in the modeling. So that's just in principle how it's set up. Questions about that?
None so far.
So the output is either the total transmittance, like this one, or the total radiance. For the transmittance, it also has the transmittance due to scattering. So the scattering functions are in here. So this is really what's the reduction you get along the path of the radiance. So things which are scattered away are also part of the transmittance. It's a little bit, yeah, sometimes confusing. That's not of importance now. That's just accuracy considerations for spectroscopy. For the standard atmospheres, this is what you have in the normally in the standard atmospheres. For these 6 of them, you can select. So they all have to say a fixed water vapor amount, ozone amount, and temperatures and pressure. That's the main parameters. Moreover, they also have a fixed amount of certain gases. So here you see the variation of the CH4 for the standard amount in atmospheric centimeters unit. So this is grams per square centimeter. I think it's the same as atmospheric centimeters. So the whole column from the ground to the sensor is this CH4 amount. Yeah, if you want to change it, as you see, the variation here is very small between the various atmosphere of CH4. So that's why you got to scale it differently. You start with 1 atmosphere, and I sent you this example last time or after last time. And there you can say, I want to have double as much or half as much CH4. and then you see what signatures you get at the sensor. We can try to do this afterwards for Sentinel and see if there is a signature at all. And that's what you do as what I call a sensitivity analysis. You do a series for atmospheric. In this case, it would be an atmospheric series, and you extract it, and then you. That's how you get a total. You see if the sensor radiance really reacts on a constituent. That's the one I showed last time, but here CH4 is not in, so that's why you cannot use it for CH4. You could use it for different parameters. But what you get is, for instance, sensitivity to ground altitude. Then you see that because the absorption of gases depends on the ground altitude, because you have less atmosphere between the sensor and the ground if you're at higher altitudes. And so this will also be the case for CH4, of course. If you have higher ground altitudes, you will get a less signature of the same amount. Or you will have a signature of CH4 if you go from 0 to 2000 meters. That's something for geology. It's also not of relevance now. Something which also is maybe of relevance is the U-angle effect. So it's also called the panoramic effect. In Sentinel, you have a big field of view, so you go off nadir by a few. I don't know by mind, but I thought it was about plus minus 20 degrees or something. Do you know by mind? It's quite large field of view, plus minus 15 or some. It must be in this range. And plus minus 15 means that you already, if you see here 180, you can get errors or differences in a range of 10% in your radiance if you go minus 15, or even 20% if you go minus up to 20. So the rule of thumb is the percentage of deviation is about the degrees of difference. So if you have 10 degrees of difference, your error will also be about 10%. And with 20 up to 30 degrees, that fits quite well. These two things are, that's adjacency consideration. That's not important here. That's also the more spectroscopy related stuff. Yeah. Yeah, I think that's it for the theory behind Modtran. That's all. Because in Modtran, most discussions happen if you really do spectroscopy, if you go for very high spectral resolutions, because there you get significant differences depending on the configuration of the atmosphere and the solar spectrum in the background. But for multispectral, such discussions are not required.
Excuse me, Daniel. Can you go back to the slide where it has the vertical column values?
Yep.
The table, the constants, right? For each of these model, where does one obtain the values? Is it from the McClatchy standard atmosphere?
Yep.
Oh,
in atmospheric centimeters. Yeah.
So so it's a constant then.
Yeah, it's constant. If you take the McClatchy atmosphere with 0 meter ground altitude, it's constant.
All right.
If you increase the ground altitude, you will get less. So it's scaled with the ground altitude, because you have less atmosphere if you go further up. Then you also will get less gases. And this table can be found in the Modtran manual as well. That's taken from there. Okay. Any other questions regarding this fundamental part? Let me see if I got more information for you. I think that's it for now.
Another question while we're at it, for the sensor response functions, right?
Yep.
I know I noticed that for Sentinel 2 you didn't put it in the zip file, right? And
Yep.
usually, um, where where do you usually like obtain the SRFs for some of the satellites? Because I've noticed that not a lot of satellites were provided
Yep.
in the yeah. So is
I
it, where do you usually get the SRFs file?
usually I'm getting them from the satellite providers. So you have really to dig in their data descriptions or asking them directly. We have most of them for the ad core in the distribution of Modo. Maybe some of them didn't go into there. So if you need a specific satellite, you can also ask us. We have quite a collection, but we didn't put all of that in the distribution of Modo. So we
Oh,
could
all right then.
so this
Okay.
can be put in later. Let me see if but Sentinel, I think in the meantime I put the Sentinel part in there, but it's not yet, pushed to the server, I think. But you received the ones from Sentinel, isn't it? In the me, I sent it to you.
Yeah, we have already
Yeah.
received that one.
Mm. And if you need others, you can first search on the websites. It may also be that they are updated after a while. So some of them, it could be that in our distribution some of them are outdated. So
Mm-hmm.
because we don't update the distribution regularly, or we just if we once put it in and we left him as is, and it can be that they do recalibrations of their sensors from time to time, or if they find a better response function. So there is no warranty that these are the best ones, the ones we are having in the distribution.
All right.
That's just what we had at that time. Other questions?
No questions for now.
Yep. Then let's go. Maybe that one can be closed. And I'll go over to Modtran. And maybe the first thing to check out was what the thing with the CH4, isn't it? So should we go directly to that? Yeah.
Yeah,
Yeah,
sure.
And
can.
and I have this JSON file which was given here, which I sent you last time. Where was it? It was here CH4. Um, this one. No, that was the tape 7 output. I wanted to show the JSON. So what I did is, so the trick was to put in the atmosphere to have this C_prof set to 1. So that's scaling the profiles. And the models is atmospheric mid-latitude summer. So this is the base number for the amount of CH4. And then you have the so-called SU mix parameter. And the third entry, 1, 2, 3, this one is the one for the CH2. If it's 1, then it's exactly the number I've shown before. Then it's the one from mid-latitude summer. And then now I put in the first one, it's 0.5 as much. So it's much less. And then this is the first run. This is the second run. So in JSON, you can put them together into one file. So whenever a new Modtran starts, you can just copy paste the whole JSON. No, new Modtran input, sorry. Modtran input starts again. Here is Modtran input. This is the first input, and the next Modtran input is coming down here. So there is a new one which starts now, a new run. And this now has a 1 here, so that's a standard number. And then there's a third in the file, which is coming somewhere down here. Again, Modtran input. Here it is. Third one starts here. and now we have a factor of 2. So the simulation was 0.5 as much, 1 time as much, and 2 times as much CH4 as the normal. Is this
So if I want to simulate the, let's say, twice the amount of CH4 at atmosphere, should I use
Yeah.
the last one?
Yeah, that's the last one now. And but you can run all of them together in Modtran. So you can run it will run 3 times if you with this input file I sent. So this so that makes it so you could add as many as you want. You can also add 10 of them, but in one JSON file, and always with this Modtran input tag. And again, so you have to just copy this again further down.
So I
And
just
now
need to copy the same part
Yeah.
and change the value of CH4, right?
Yeah, you just change this file here. This is now for
Just
3
change
runs. Yeah. Then you
Just
can
change it from 2 or to 3 or 4 or 5.
yeah.
Okay.
That's why there would be the other gases here if you go for the Modtran manual, and then you search for ES UMix. That's this one. Here it is, the description. Here it is, cprof. That's the first. That's the flag which tells you what to do with. So this is scale uniformly mixed species using this SUmix input array. That's what it says here. And that's not the easiest way to do it. There would be with exec. That's I think there you can use. What's exec? That's something I don't know, but yeah, that's why we use just one. And then you have 10 parameters. Here it says SUmix 10. If cprof equals 1, then it will read those, and then you see the 10 gases which are in here. And this in bracket is the sea level mixing ratios. That's not the scaling. That's not the atmospheric centimeters. So you see, and 2 and 2O, CO is the first, the second, and the third one is CH4. And then it's O2 and so on. So you could also change the other gases by this factor.
What does the value in the bracket represent? 1 and 7.
Yeah. 1.7, that's ppm per volume on the ground. That's just, and it's going down exponentially with height. Then that's not the column. That's not the column. So you could also use that one. It will also be scaled. This one, of course, will also be scaled. So if you were more interested in the ppm value, you can start with that one. With factor 1, you have 1.7 ppm per I think parts per million. Yeah, on the ground. And that's how you. Yeah.
Is it possible for me to like set the altitude, like say I want it 10 meters above ground?
Well, this won't make a big difference if you go from 0 to 10 meters above ground. It will only the layers. If you go further up, then you have a different fundamental mixture because of the various weights of the gases. They are mixed differently at higher altitudes. So CH4 is, I think, it's 12 to 16. It's lighter than air, so there will be more CH4 at higher altitudes than in ppm than at lower altitudes because it's less heavy.
So we need to know the specific value of ppmv at different altitudes for us to be able to do this.
Yeah, then you will have to analyze maybe the tape 6, that one. And then you will see the profiles. So this is written if calling this JSON. So that's the tape 6. And then you have the atmospheric profiles here. These are not the ones we need. And Let me see, I think further down the gases are coming. And here you see the CH4 at various levels. So this is atmospheric centimeters per kilometer. So that's partial column of the yes, from this you could it's also grams per square centimeter per kilometer. So you could transform this into need some little bit physical transformation into ppm if you want. So you have to look up how to transform to get from the atmospheric centimeters to the grams.
ppm.
Yeah, to the ppm. That's a transformation. One would need to write it down to get this right. But there you see it's CH4 is not always the same. So it has it's decreasing. No, it's decreasing. Yeah.
Yeah, it's decreasing for increasing.
Well, everything is decreasing, but this is absolute atmospheric centimeters. That's the absolute amount. That's not the ppm. The ppm will, of course, has to be compared to the average, and I think the pressure, the average pressure derived density of air at this height. So, but that's the table you want to read if you really need the full profile.
That's the one.
That's the first one, and you see you got 7.88 here. This was the one with 0.5, and now we expect that the next one will be double as much. So let's go further down. Somewhere the second profile comes up. Is this the second one already? 7.32. No, that's not the second one. That's still the first. And it's all the data simulations, and after that, the second one should pop up. Now it's that's the second run. And now we have again the same tables in the beginning. Where was the CH4? I'm searching for the CH4 again. Here it is. And now you see it's double as much. Before it was 0.7 times 10 to the power of minus 2, and now it's 1.5 times 10 to the power of minus 1. So this would be for the second run. The first one was factor 0.5. The second one was 1.0. And the third one will be 3 times 3.1 or something like that. The last one will be somewhere that's, again, I'm going through it. And then the third one, that's here it is here it is 3.1. Yeah, that's the last one. So it's scaled exactly against each other. That's how you find it. Now to this parameter, I'm reading it now. You cannot read it. I have the 3 runs here, and you cannot see it in the GUI. That's what I mentioned last time. The only thing it says, you have the profile scaling. This is this flag. It says 10 molecules are scaled. That's where you set it. But afterwards, and you have to enter the scaling factors manually. That's but you still can browse. So you can go through the various runs down here. So it says it's 1 of 3 down here. So this means there are 3 Modtran runs in this tape. And now the first one is shown. This shows the second one. This shows the third. Here you won't see any difference because this the scaling factor is not shown in the GUI. But still you can run it now from here. The last time I was trying with the profiles. With profiles, this is not feasible, but with the scaling factor, it's feasible that way. You could also, of course, change other parameters. And if you push this button once more, I can add a copy of the last one. And now I have 4. I can save this one, save as triple. I do 4. So now it has 4 runs in it. Oh, okay, no, that was not save as only select. No. Should use the other one again. Sorry, save as only makes a clone of the current run. I'm running that one. 4. Then I have to. I can do it that way. Add one. Okay. Add one. Okay. Add one. Okay. Now I have one with 4 runs in it, and it didn't save yet. Sometimes I have to just enter here, then I can save. Okay. And now I can done. If I'm opening this JSON file, which has been, it should be 4 JSON, that one. It always has a 2 now in, because it was the last one I had open. Now it has always a 2, 4 times. And now you could change it again. So that's how you at first create a multiple run JSON, and then you can change parameters inside the JSON. That's and now if you run from JSON, I take the triple again. So if you want to run it, you just say run from JSON. I use the triple. Okay, and it will run it and create these 3 Modtran outputs. The one again. Now, how to extract the data? Is this okay for the setup?
For this one, are you doing transmitters or solar and thermal?
Transmittance.
Yeah, transmitters.
This one I was doing radiance. Yeah. If I want to do transmittance, I can go this way. Set up JSON. Yes, I'm opening that. And now I'm doing a save as, making a triple transmittance. Okay, now it created again 1, and I change it to transmittance mode.
Yeah, I'm confused a bit because at the mode there, right, there's no radiance. There's only solar radiance. So should I select solar radiance when I want to do radiance, or?
No, it's solar and thermal for radiance.
Solar and thermal for radiance. Okay.
It's just to solar and thermal radiance. It would be, and thermal only. These 2 are radiance.
Oh, okay.
So they're synonymous then.
Yeah, thermal. That's only thermal, and solar and thermal. That's it does both. And this irradiance is on the ground. So if you want to know what's on, and lunar is if the moon is the source and not the sun.
So if we were to just simulate radiance, we don't have to change then the solar and thermal.
If you want to do radiance, you select solar and thermal.
All right. Yeah.
And if you want to do transmittance, then you select transmittance.
All right. We were confused because we thought we had to choose amongst the options to generate radiance. But yeah.
No, it's just this switch. That's the main switch here.
All right.
It's just solar.
Okay.
And now you have the same parameters as before. You have the 10 molecules still here, and I can do the same game again. So I'm adding 1. Yes. Okay. Okay. Adding a second one. So it copies the current one into and now I could also open that one. The trans, where is it? Trans JSON. And it has now always 0.5, I think. So I can change that one. To edit it, I need open text file. So you can also edit it externally, but if you want to edit it internally, you cannot edit in this window. This is a display only. So where is it? The trans was here. So I'm just changing it. I'm leaving it 0.5, taking the same values as before. So I'm entering it 1, 0, and 2. There was 2. That's the last one. 2 and a 0. I can save it. All right. So now I can run that one. I can also run that one. Will run from JSON. I'm using the trans now. Okay. Transmittance is much faster than radiance. That's so I think it should be okay. To see if it was okay, then you can always run transmittance tape 7. there was a problem. I wanted to plot tape 7. Oh, sorry. Modtran. Where was it? Plot, here it is. That one I wanted to run. So this will just do a standard plot of all transmittances in here. And so this apparently worked as it should. CH4 is not in the standard plot. Yeah, you have to extract it and plot it separately. But here you see if it worked correctly, and then you have all transmittances for this situation. Here it only takes the first run. If it has 3 of them, it only plots the first one. You cannot select which one to plot. That's just for a preview and a fast check if it worked as it should. You could also say take the radians, that one, and plot, then you will get the radiance plot of this situation you had before. Or the components at the same. So that's, for me, that's usually my first fast check if it was running as it should, the correct range and so on. And then one can go further into the analysis of the data. That was, the function was plot tape 7 output. Now next step is extraction of spectra and appending the spectra and convolution. So this, because we have to do it manually now. So the next step is extract spectra. I'm using now this triple tape 7. And I want to have the radians, the default column that's given here, so you don't have to change anything. And the minimal resolution 0.1 nanometer is good enough for your case. So it just extracts this data to spectral columns, and I'm calling it maybe just calling it radians. CH4 radians. Okay. And now I think the CH4 radians files have already been created. So you can have a look at this. This one is the first one. Now we created 3 files because we have 3 runs. So 3 of them. And here is the total radians, and you can do a quick plot of that. A quick plot of these radians. That's what was output now for the first run. Usually you want to have them in one file. That's why you have to append them. That's an old interface, but you can just add them at the second one, at the third one. And then you can append them. And it will just radians, just without the number. That's already done. So now you can do again a quick plot of radians all. And now you see this little difference here. That's where the CH4 is. It's only here is a little bit of a difference, and here's a little bit of a difference. Everything else didn't change. So CH4 is a very small signature. Even if now we have a factor of 4 more or less CH4. That's why I'm asking, are you sure you want to do this with Sentinel? Because it has very little impact on the spectrum. We can now we can go further and doing a convolution to Sentinel. We have this spectral input file, that's this all file, and I'm selecting the response file of Sentinel-2. Where is it? The 13 channel, this one 2B, I guess. And then I do the convolution. It will add an _f if you don't say anything. So it's done now. Now you can have a look at this. Show text. This is the F file. And here you see the differences, what happened. And the signature is given in this band has a little bit of a variation. And the 2.26 has some, this is, I think that's significant. So we can do again a quick plot of that one. hardly visible. In the numbers, you see a little bit of a difference here. You see 2.4 to 2.38 at 1.65, 0.8, 0.008. The problem is that these are very small values and you should scale it. This plotting here is not very flexible, this quick plot. That's why it's called quick plot. If you want to do it inside Modtran and do this analysis, you have to create a spectral library. You know spectral libraries from Envy, I guess. You know, so you can always export spectra to a spectral library. So you select all this, and I'm creating all. Now I'm giving it one has to make sure, often change the name also in front of the extension to avoid confusion in Envy with extensions and yeah. So these spectra have been exported now to a small spectral library. And now I can plot spectral library, and this is much more flexible. Now you have the spectral library, and you can change the graph, the y-axis. So I say I only want to see up to 0.01. Now you start seeing the differences here at the back. Maybe y-axis can be 0.02. Then yeah, then you see a little bit more than you had before. The reset range, you also see it here already a little bit. These are the individual data points, and that's where the variation is. But this is how to deal. The same can also be done. Maybe export spectra with the unconvolved spectral file, the ASCII file. So that one can also be exported. All the other was okay. Then you can do a spectral plot the spectral library. This is the one without this one has now all the spectra as yeah, and then you can change whatever you want and so on. But you have you could see what the spectral signature is. I want to now maybe I want to know what's between 2000 and 2500. Then I change the x-axis from 2000. It's just comma separated. It's now here. And then I want to change y-axis from 0 to 0.03, huh? Now this is your CH4 signature from this variation. That's what now it's really visible in the spectrum. And I think Sentinel has its response somewhere here, 2.26, I think. So somewhere here. So this means in principle it might be visible, but of course you will have a lot of crosstalk. So how to distinguish the brightness of the ground from CH4? I don't know how you want to do this, but there will be, because you don't have a reference, you don't have Sentinel only has a band here and the one at 1.6.
Yeah, 1.6 microns. Yeah.
Yeah. So you cannot, you of course this will be in your data, but and you might see this over a very homogeneous area. So if you have a desert or something, it might be that you really see the signature of methane. So if you have some methane leak in an oil field, this might be visible because the desert is very uniform, and this variation might be visible. But in forests also you won't have a chance to see this. That's yeah.
So that's the output that Modtran can create.
Sorry?
So there's the output that Modtran can create specifically for CH4 using Sentinel-2.
This is what Modtran can create for Sentinel-2. Yeah, that's what you
right?
see. Yeah. You asked for, yeah. Now, if you want to analyze this, yeah, one will need to create some ratios or so on. So if you want to do an image file, I have some, no, it's nothing here. Here up. There's a small, that's Landsat, not Sentinel, but it's comparable. It's just to show you if you want to analyze an image. There's this file viewer. It's also just show display env file here. And so I don't know, you have env licenses as well.
Yeah, we do.
Oh, okay, then it's not of that much of importance. Then you have a lot of tools to analyze your imagery and to do that. So just to show you, here you could also do simple band indices and so on, can be done also from this GUI. And some classification with speckle angle mapping, for instance, can be done here. And yeah, if you want to have a absorption depth, this is what you usually do with satellites. Then you would, or with gases, you usually want to know how much absorption you have. You need more than one band. You need one as a reference, and then you can do it. Otherwise, it won't work. So it would be a band ratio at least. It's the easiest way to do it. And if you take the 2.2 against the 1.6, that would be the same as you'd do with Sentinel, I guess. Then you get a band ratio like that, but of course you will see the ground because the ground has this signature as well. And then now how to distinguish this from Sentinel. The one thing which could be done, well, one thing which could be done if you have a database of old images. So if
What do you mean by that?
So that's something which with satellite images, often you have the same area covered more than once or over the years, every year again. And so you could, and you know that now we have a problem with CH4 and we didn't have before. And then you can analyze the difference to the year before to see if there was a difference in these speckle bands or in this band
So like a
index.
time series then.
Yeah. So then you do this band index for all of them and analyze the band index against the situation where you know there was no CH4. This might be possible, but also there you need quite a lot of CH4. It's not about trace gases, it's about a massive leakage of an oil field or something. That's something you might see then.
Let's say if I have a satellite Sentinel-2 imagery right over a place, and is it possible for me to import that image into this GUI here, or do I need to use
this,
NV for that?
you can use Scanvi, but you can also import it here. So if it, let me see if I find a Sentinel image. I got some Sentinel here. It is a Sentinel. Maybe that one. 20-meter BSQ. I think that's one I imported already from a TIFF. We import it directly. Usually it counts as a TIFF. Let me see if this is implemented in this GUI. Import. You have just a moment. I will start something else for you. I'm closing this. There is always in so there is this. Maybe I'm opening that one again. But there is an import function here. Is TIFF import? There should be a TIFF import as well. Export calculated the index profile. It can display TIFFs directly. That's one thing. Let's see if I find the original TIFF of a Sentinel image, if this is imported. I'm not pretty data satellite Sentinel-2. Maybe I take an old standard one. Granule. Oh no, it's JPEG 2. That's what they have as a standard. Yeah. No, the import is not supported here. So you'd have to, if I'm opening that one, it will only open. Yeah, that doesn't work. The only thing which is supported in this GUI is really TIFF and ENVI files.
TIFF and
TIFF, GeoTIFF and ENVI can be imported here and shown and analyzed. But anything else needs to be imported maybe in ENVI or wherever to, if the Sentinel original data are JPEGs and they are coming one band, one file only. So you have to integrate them into one file at first. That's something we do in the AdCore module. So if you do for MSI correction, we have this routine which takes all the Sentinel files and puts them together nicely. But that's not something we have in the standard in this package. So this Glimpse software, that's a free software we're providing for education and for universities and so on. That's so but it's limited in functionality. That's just for browsing ENVI images if you don't have ENVI licenses enough. So that's something you're free to use.
So let's say because we do have ENVI license over here, and we do have a Sentinel imagery over region. So do I import the imagery into the ENVI license and convert it into TIFF file, and then I can bring it here? Is that right?
Yeah. So if you import it in ENVI and save as an ENVI file, then it can be used with our software. That's also something else I want. That one I can close down. I go back to the Modo 6. Or maybe just to have walked you through the CH4 stuff.
Yeah,
now,
sure.
Yeah. The question is, what next? So what else are you interested in?
The one that I just recently asked, how to integrate, how to use the NB files, because let's say I have an imagery right over a place, and I want to be able to convert the simulated radiance using Modtran and the measured radiance using NB. Is that possible?
Well, what I just have shown you, I have convolved it to the Sentinel. So these values you have feeds to the Sentinel imagery, and this should be okay. And the other question is if you're also interested in atmospheric correction, if this is also a topic in your case or not, or if this.
I don't think AC atmospheric correction is of importance. Yeah.
And so the question is what else is how to analyze your data, or what else would you?
Because let me explain to you our main methodology here. Because we want to use Sentinel-2's imagery. We have a few papers that we're referring to. We want to use Sentinel-2's imagery to detect methane, which we were able to detect in some places a very large plume. And once we're able to detect it, our next step is to make a simulation using Modtran. Make a simulation using Modtran and to subtract the radiance created by Modtran by using the measured radiance. Can you make it make sense?
I didn't get it yet.
Yeah,
So-
yeah. So that's what we want to do. We want to make a minimization using the measured radiance using the Sentinel-2 imagery,
Mhm,
and also by using the simulated radiance using Modtran.
So you want to match it as good as possible.
Yeah.
Okay, that's so then it comes also to the Sentinel calibration. So,
Mhm.
but if you, I think if you download the Sentinel imagery, it's usually coming calibrated, isn't it? So it's coming. So you have the sensor radiance which is fitting, and then you can do a direct comparison. Um, it's let me see what you have here. I'm just browsing the Sentinel imagery I have here, or maybe you can show me what you have so far. Um, Let me see if I'm going to. Uh, I'm searching for the.
Excuse me,
Just,
Daniel. I think to be honest, our end goal is basically to quantify methane from our satellite imagery, right? And so for now, we're in the midst of basically relating the radius transfer with our imagery, right?
Yep.
And so we're kind of in that uh in in a problem right now because we cannot see how the radiative transfer like Modtran can be integrated with our imagery. Yes, we know we can use NV and to generate
Hmm.
spectral library and whatnot, but um in the end
Hmm.
the end is the output is a graph, right? So what we're stuck on is how do we relate the obtained graph to our
Hmm.
image sentinel imagery. That's the problem right now.
Yeah. So that's there you will. I think there you will have to maybe stop sharing here. Um, so there I think you will have to uh, first of all put on paper how to compare it. So you, as I said, the simplest way is doing ratios. I don't see much else you can do, and
Mm-hmm.
or having one is having ratios, or the second thing is to have well-known targets.
Yep.
So if you have a well-known target, which might be sand or whatever, which is measured, or you know the brightness exactly, more or less exactly, of a certain area in your. Is it about for Indonesia, or is it for which area?
It's for Malaysia.
For Asia,
Yeah.
it's mostly forested, so there will be very little stable areas in
Mhm.
Malaysia. I guess it will be
Yeah, the
quite difficult.
conditions aren't very forgiving.
Yeah.
So that's the problem.
Yeah. So maybe over the cities it might be easier than uh, over the forests. So if you're searching for methane, it could be the time series over the cities will be the trick. So because the cities, the buildings remain more or less the same over time, spectrally. The brightness should remain more or less the same. But then you will have to consider the time of the year, the solar position for all those, and normalize it to the same solar position, so by cosine correction. And then you can compare this to again amongst the various images. So that's I think that's the a way which might be possible to see something. But I'm not sure if the methane you're after is in on the countryside or more in the cities. That's yeah, something to be checked. I'm not sure. I don't know your use case. And for the comparison, the direct comparison, one thing is really it comes down to calibration. So how to
Mm-hmm.
calibrate the data against each other. So the unit of Modtran, what you get as an output, is always milliwatts per square centimeter steradian nanometer.
Mm-hmm.
So it's also given in the descriptions. So so there you have to be careful if comparing directly to Sentinel data, what units they have in the Sentinel data. And I'm just wanted to check this out.
Yeah, so like
Um,
for our region of interest, I mean, I cannot disclose the actual location, but it's mostly offshore location. So that there's a lot of there's a lot of underlying problems.
so you have the water as a reference.
Yeah, like so there's a
It's
lot of
opposite. Yes. Okay.
interference with the sun glints and all.
Mm-hmm.
And so far, we have managed to obtain the reflectance of methane. We have managed to detect methane actually by using Sentinel-2. It's just that we are not. We are so far we have managed. Can you hear me?
Yet now it's better. Yeah.
Yeah. So far we have managed to detect methane by using Sentinel-2, but it's just a reflectance. We want to be able to correlate it with the simulated radiance here by using Modtran.
So you only received the reflectance data for Sentinel.
Yeah.
So but you always can also download the radiance data for Sentinel. So the level 1C or 1D or whatever it is. But
L1C.
yeah. And then you would have to work with that one. And I just checked the I think there is a factor of 1000 from what they have to
The
the unit
quantification
we need.
value.
Yeah.
Mm-hmm.
So you have to divide it by 1000, then it should be comparable to the output of Modtran.
Okay, so let's say I mean I can do it right away.
Maybe you can show me an image then. But if you have a radiance image, then yeah.
Give me a sec. Because I usually we in our institute over here we usually use either ArcGIS or NV.
Mm-hmm.
So let me use ArcGIS for a while. It's a lot easier.
And
so for Modtran, it's a lot easier to use NV, is it?
For Modtran, yeah, for Modtran it doesn't matter because Modtran is it's only for the spectral libraries. It's NVIDIA what you output. But if you talk about these 5 numbers or 13 numbers from the simulations, so to put up a model can be done everywhere afterwards because you only have you saw this little table you receive from the variation of CH4. And this is you need this table to create a model which can be applied to the image, and the model can be done in Excel or wherever you want. It's just you want. In fact, in the model it will say for this amount of CH4 we got that amount of index. So this and the same index has to be done with the imagery, and then that's how you relate. That's what we call a model calibration. So usually you have the simulation of a gas at various levels. That's how I showed you how to do that. And this variation of the gas can then be compared to can then be put into a function which has an index on the y-axis and on the x-axis the amount of a gas. And the function is usually a ratio or whatever between multispectral bands. For instance, 2.3 against 1.6 or 1.6 against 1.0 micron meters band in Sentinel. And if you have this function, you apply this function to the image. You do the same ratio in the image, and that's it. But if you're offshore, you will have to work explicitly with the sun-glint areas because the water itself has no signature.
Yeah.
So you need sun-glint, otherwise you cannot see it. So you have to search for bright areas. And then you have to filter out the water. So you only take the bright pixels. And then what you get is what you get is a solar spectrum which has always the same signature. And I think this might even be a good case because the solar spectrum is constant. The ratio between 1.6 and 2.3 is the same, but if there's more CH4, it may vary. So I guess this one could try this. So just select the brightest pixels you have in a certain area. But so you need to program something. You have to do a filter and only search for the bright pixels.
Yeah.
Take the spectra of that and compare it to your index. And in Modtran, in the simulation, to compare this, you'd select a bright object. So you do the simulation of CH4 with, let's say, 100% reflecting. So in Modtran, because we did the radiance now, I think I don't know which reflectance I used, but I could just see it again, look at it again. It was template, was that on? No, it was the wrong. Go for the CH4. There it is. The triple solar and thermal. It says a where is the reflectance? So what solar constant? Modify arrow. Lambert 0.4. So I have 40% reflectance. What I assumed in the. So that's I can share again just to show you. So if you want to compare it to your SunGlint data, I think 100% like a mirror is, well, it's maybe okay. Maybe it's a little less in average, depending on where you put the threshold for bright pixels. So, but
Daniel,
that's,
I don't think we can see your screen for now.
yeah, I just start sharing again. Just a moment.
All right.
Here it is. So you see down here, it's the Lambert, constant Lambert, it's the reflectance. It says now 40%, 0.4. So
Okay.
I would set this to maybe simply 1.0, that is 100%. Save. And then you go to the next one, and so you can that's too I do it in JSON, that's too complicated that way. You can see it in JSON as well. Edit, open text file. Where is the triple JSON? The triple JSON, here it is. I need my glasses again. So in the JSON, you see the reflectance, there's a geometry, the surface. Reflectant constant, that's okay. And then here it's 4 minus 1. So will be 1.0. I just would put in 1.0. That's it. So ref, that's surface reflectance. It doesn't make much sense to include a ground spectrum in that case. So because it's like a mirror, so it does continuously reflecting temperatures and so on. And then you have to do it for every of the runs. So it would be 1 here again, 1.0.
May I know like what's the rationale behind putting 1? Like, is that what does that indicate?
So you said you're analyzing water offshore, and if you analyze SunGlint is a reflection on the surface, and it's usually reflecting 100% of the radiation, so it doesn't absorb a lot because it's like a mirror. So that's why 1 is maybe a good approximation. Maybe it's a little bit too high. So because usually in 1 pixel of Sentinel, it's Sentinel. Well, one has to be careful. In Sentinel, you may have Yeah, maybe 0.5 is also fine, or 0.8, because you have big pixels. So you never have only reflection in the pixel. But you could use something like a large reflectance and only select bright pixels. Then it's because that's the rationale is really that it's assuming a mirror reflection and analyzing this data, only the bright pixels in Sentinel. But I'm not sure how much sun glint you really see. So if you have sun glint areas.
So one can dictate how much the reflectance values are then according to the locations of the imagery, right? So
Yeah.
if it's so let's say if it's ocean, then you said uh the value 1, right? So let's say if it's for like a huge leakage, right?
Yep.
Like ground, then it's probably going to be lower. So 0.5.
Yeah. Yeah. No, it's really it depends on the procedure. The idea I outlined before is selecting only pixels which are
Yeah, high,
bright,
right. Yeah.
high values.
Mm-hmm.
And so those and you think about an oil leakage, not on a methane leakage. If it was an oil leakage, well, then you have a problem. Then you cannot do it that way. If
Mm-hmm.
it was only methane leakage, this won't affect the ground reflectance at all, and
Mm-hmm.
so you could use a higher value here. With
Mm-hmm.
oil, I think, yeah, this will be will be difficult because there you won't get any sun glint anymore if you got an oil, and you will
Mm-hmm.
have a lot of absorption, and it will be not a constant absorption. So
Yeah.
oil has a specific feature. So that's why, yeah. But
All
the
right.
rationale was really to think about sun glint and methane only.
Mm-hmm. Okay.
So that's just something to think about if you want to simulate or calibrate a model. If you do by the way, if you do a ratio anyhow afterwards, the brightness is not that important. So if it's the brightness would be important if you want to analyze the absolute value of in the data. But I guess absolute value won't be feasible at all. You cannot simulate the absolute value over water because every pixel has a different brightness due to variability of sun glint.
Mm-hmm.
So that's just what else can be played with. That's okay
I
here.
have a question again. When you click the run from JSON file, right? About picking the spectral library, if I'm not wrong. Did you only pick the first file instead for the Sentinel-2 files, right? You only pick the
That was
first file.
so at first the run from JSON is not aware of Sentinel at all. So this just runs the full spectrum.
Mm-hmm.
This creates the full spectrum in the range of Sentinel. So that's just what's given here from in the last part here. It's always the same numbers.
Oh, so it runs
Spectra
throughout. Oh.
V1 to V2. That's from 395 to 2.7. That's but this is in wave numbers, by the way. That's not
Mm-hmm.
in
Yeah.
nanometers. And afterwards, it's in the extraction. The procedure was really first to extract and then to append and then do the convolution.
Convolution.
And only here, I'm selecting the first response file,
Yeah.
and then it will convolve to all. It has so should have a series of response files like that, and so it will find the others. That's how it's found. And by the way, for your analysis, you also have in this in the where was it? In the sorry, I should go and show here. Uh, show system file. Here you get into the installation. That's easier. You have the sensor response. and then you have the Sentinel-2, 13, and there's a file called E0. So this is that's the solar constant for each of the bands. And so here you have the 1.6 and of the Sentinel-2. That's for an average condition over the year. So this does normally not change a lot. It's only the distance of the sun which makes a difference here. But you'd have the 2.1 and 1.6 value. And so for if there was no methane, this relation should always be the same, because this if you're talking about sun glint. So if we assume sun glint reflecting constantly, uniformly, then the relation between these wavelengths should remain constant. And if there was more methane, the relation between 2.1 and 1.6 would be lower, because the 2.1 will go down a little with more methane. You get absorption there, and then you would get a value which is slightly lower than what you have here. It will be, but the signature will be in the range of about 2 or 3%. So still, I said in the beginning, one can try, but I wouldn't promise that it works. It's maybe what would be maybe much more of an idea is, did you ever think about using Nmap or emit data, so like the spectroscopy data cubes?
Yeah, we've heard. For now, we're mostly focusing on Sentinel-2. Sentinel-2 for methane detection.
Yeah. So you can do this analysis, but finally, people are really doing a lot of methane stuff with the new space-bound spectrometers.
Yeah.
And that data is also available for free, but you don't get, of course, the time series.
Yeah.
So in Sentinel, you have a better time series. That's the advantage there. But it's just for further work or further involvement of this project. At some point, I think you will have to go for a spectrometer.
So after obtaining the convolved graph, right? I'm sorry, but like, how do we go about relating the convolved graph with the actual satellite imagery, I suppose?
Yep, where was it? Where was it? That one. TH4 radiance convolved. That was the convolved part. Now you see that you have the 2.3 divided by. Now you could, these two, just the simplest method would be a relation between these two bands. So what could be done is just copy that, take it to Excel, and create a calibration function. So have a new Excel here. So here you have these values. Just copy paste them. This one is wrong. And these are the three values. You know that this one is 0.5. One would need to find a real value, and these were the three values we simulated. And then you can do a calibration function, which is, let's do it, take it down here, which is simply the relation between that one and that one. And that one, just move over like that. And you see it's going from 0.33 to 0.32, so it's a little bit of variation, but not a lot. And of course, you can create a little graph of that. And so this is your calibration function, is this thing here. This is the CH4, and this is the index. Now you have to do an image analysis. So you take your image, and in the image you do the same relation. You also do this was 1.6 divided by 2. I should do it the other way around because I want to have higher index if there was more CH4. So I do it this way, that one divided by that one. That's better. This way around. So it's C. Yeah, that's correct. I was correct. Yeah. No, it's now it's the lower the value, that's the more CH4. So I should maybe do it the other way. That's why I should done this way around. I inverted 16 divided by 17. Then I go this way around. Okay, now you see it's increasing. And now you do the same index so you use your image, do the filtering of the bright pixels only, take the average in a certain area and do the same calculation. And these two should be comparable. So, and I doubt that they will, but they should be comparable if you have a uniform reflectance on the ground. So if it was sun-glint, then you would get similar values from the image directly. And then you can just get the CH4 amount for depending on this ratio. That's how I would do it. I guess you will need a little bit of programming to do that, or NV scripting, whatever. But yeah.
So that's how you
Or is
relate the bright pixels, the segmented bright pixels with the Modtran output then.
Yeah, this is the Modtran output, and I know this is the ratio in Modtran, and the same index has to be found from the image. And you know how much CH4 you had in Modtran for this index, and that's it. And here you get a variation of about 3%, isn't it? Yeah, it's from 0.1 on 3 makes about 3%. Yep. Any other?
So Daniel, I would like to clarify on this. Okay, so the the segmented bright pixel, they should be in radians, right, for the imagery.
For how to do it in the imagery, or
Yeah, I'm doing it in radians. So let's say I have the segmented pixels in imagery. So I just need to get the values of each of the bright pixels, right? I need to get the
yeah,
values of each of the bright pixels and need to do the band ratio as we did just now. And
yep.
that will give us the
And
main thing.
and for sure you will have to average quite a few pixels. So make some statistics. Otherwise, with one pixel it won't work for sure.
Yeah.
If you take 100 pixels, it might be better. Even might be feasible.
Yeah, I'm
But this
taking
will
a
be
large amount of pixels. So it has to be done for both 1.6 and 2.26. And once I get the index right, I can make the graph and it will show me the differences. Is that right?
So you can always do a ratio, as I showed before. I think there's also a band math function in Envy where you can do ratios and maybe filtering as well, where you can just take the bright, putting a threshold and say you only use the ones which are larger than this. The program, or if you have some programmer in your group, then tell him to do a little program for that.
Give me a sec.
Yep. You're searching for a function for this, so
yeah.
Because myself, I always do the programming. I don't use Envy for such stuff, but yeah.
So okay, so I get the radians and I need to make the comparison, make the index. Just to clarify, I make the index, and once I'm done with the index, I can plot the graph to see the difference. which
So
will
the algorithm. Let's outline the algorithm, huh? So first,
I'm really confused.
do the calibration. See to the left on Modtran. Is relation between index and CH4 amount. Okay, this is the first step. That's what we did in this Excel, or what I just did in this Excel. Now, select image with some, maybe with some sun glint. That's the next step. Now, in the image, you can already from the beginning create mask of right pixels in offshore area. Old at with high, so a higher threshold such that really only bright pixels are in.
Yeah.
Yeah. Now, calculate ratio between and 1.6 and 2.26. Gives you an image, and exclude pixels not in mask. We have created a mask before, mask, and then create a filter image. So if you need to, maybe you have a moving filter along the, or do an interpolation of the remaining pixels to get a spatial interpolation of remaining pixels. Gives you an image. This is an index image you receive here. So that's this index image. So from this index image, you exclude the pixels which are too dark, which are not, make no sense. And then you filter the image to get a spatial interpolation of the remaining pixels. And you could also smooth filter the image, because usually you have these interpolation artifacts, and transform index to CH4 by the function below. Right. Now we only had three. Now it could be a linear. I'm not sure if it's a linear function. If you plot it, we can just insert, make a little plot. Seems to be more or less linear, huh?
Yeah, it's linear.
That would be not, then it's quite easy. So you can create a linear function between this and that. So, and then you can use this linear function to relate the
With
index
the,
in the image to
yeah,
the CH4.
I see. So that's the summary of it then, the algorithm.
Yeah, that's how you would, it would be by the function to the right, and that would be a result. So in principle, this would be working that way, but of course, you will have problems with noise and with calibration and so on.
But Daniel, I would like to ask, okay, we use Modtran to generate the radiance, right? At sensor
Yep.
radiance. But for Sentinel-2 imagery, we would have to convert the imagery to reflectance. So since we're comparing Sentinel-2 imagery with Modtran, right? So does that mean for our imagery, we would have to convert from reflectance to radiance in order for
No,
the...
just download Sentinel directly as radiance. Don't go for reflectance. So
Okay.
you can get the radiance product for Sentinel directly and use that one.
So just direct
But
conversion. No need to convert it
yeah,
to
you can.
reflectance.
You don't need. Otherwise, you have two conversions. If you use reflectance, this has already been inverted from radiance, and then you go back to radiance. This doesn't make
Yeah.
sense. So that's
Yeah.
why you really try to get from the download Sentinel download directly the radiance to level 1C and not the 2A. So it's usually it comes like this. Let me see.
The product that we're using is L1C, and the product is already given in reflectances, if I'm
Oh,
not
that's
wrong.
1C is okay. Then let me see what I have here.
TOA
Sentinel.
reflectances. So we're just confused on how do we compare between the two, because
No,
Sentinel-2.
but here I also have 1C, and this is radiance. That's strange.
Mm-hmm.
Just to show you what I have here, I got here a Sentinel-2. It says 1C, isn't it?
Yeah.
MSI 1C, and this was. Then you go into the granule. You got the data. And you got the image data. And then you got the original, so these JPEG files. And what we are getting here, we did the atmosphere correction for that. That's why all this stuff is laying around. But it has to be radiance. It's strange why. You're sure that you got reflectance?
Yes.
Yeah.
If I want to see.
Yeah. The products are given in the form of TOA reflectances, not radiance.
But you also get this kind of JPEGs.
Pardon?
You also get this kind of JPEGs here, BB01 and so
Yeah,
as
yeah,
a
the images are of course given in DN, right? So there would be a conversion from DN to reflectances. So that's why we were wondering whether we had to convert to radiances.
yeah, you'd have to convert to radiances, but
Right?
yeah. And I'm just wondering if you're so it's a send to so it's a send to core output, or what kind of reflectance are you getting? You know that. Let me see if there is some description here.
Mhm.
Oh, betul kan?
Let me see. Just open this.
Reflectances kan? Kita tak ada radiance. Dia cakap dah ada. Tak ada.
Because we usually get the data from the granule once we get into the granule, right?
So it's the level. I'm just checking the XML file on the upper level in the safe. So it says level 1C for sure here, and this in my case it's really, and it was all here. It has the irradiance.
Mm-hmm.
Yeah, they
I
only
know.
give the radiance.
Now I know the problem. Okay, what you're getting is not reflectance. It's at sensor reflectance. You're getting apparent reflectance.
Mm-hmm.
So you get so what you're getting is the division of the solar response function with your sensor, and then it has to be back converted to radiance by applying these gains. gain values.
Yeah.
So it's not the ground reflectance what you're receiving. So level 1C is at sensor. So they store it as it's equivalent to radiance because it's not atmospherically corrected. It's only the reflectance on at sensor.
Yeah.
So that's okay. Now I forgot that they are storing at sensor reflectance.
Yeah.
And so
So
you
that
have to
that's,
yeah.
so does that mean we would have to convert then? We would have to
Yep.
do in order
So you would
to compare with the Modtran output then.
Yep. That's
So
correct.
let's say about that, right? Once we convert it into radians, and I'm able to take out the values from band 11 and band 12. Band 11 is in the 1.62 and band 12 is at 2.26. All right.
Yeah.
So
Then
if
you
you
can
notice, I got the values already. It's at 0.715 since you are asking for it. And so how do I interpolate it? Because for Modtran, we use 0.5, 1, and 2. But
Yep.
for Sentinel imagery, there's only one value that will come up.
From the image you get one value, yeah.
Yeah.
It must, you're searching for the value, you get thousands of values because every pixel has a different value. And that's how you use this function. You take your image and and do a linear function, the constant plus a gain, and then you transform it to CH4 amount. Then you get a CH4 map. That's how you do it. So this is only 3 measurement values, and then you have to put a line through that just by a linear fit. Then you get a linear function, and then you can apply that to the imagery. So that's you just do a linear function, linest. I think it's linest. Known wise, that's that one. What does it output, the linest function? I think that's one would need to look up what it's. I think this one does a linear function in Excel. It creates your linear function, which is something like. So maybe I have to. No, it's okay. Leave it out. Trash this stuff. Maybe I have is a relation between index. Maybe I have to enter this here. Find linear function, and the function is ch4 equals a plus b times index. That's what a linear function is.
So the a and b stands for
the gain and the offset. That's just for the linear function. Y, like whatever linear function you have. One is the offset, and the other is the slope, or the yep.
Okay.
And this one.
I think I can share my screen.
Mhm.
Let me share my screen to you for a while.
Yep. Stop sharing here.
All right. If you can see that, this is the I've visualized radiance for band 12 and band 11 of Sentinel. As you know, band 11 is around 1.62 and band 12 is around 2.2, right? So if you can see, this is band 11 and this one is band 12. So
yeah, now if you divide band 11 by band 12, you get a value of about 3 point. Yeah, we will see how much, but
give me a sec. Let me do that. Band 11 by band 12 or band 12 by band 11?
by band 11 by 12. That's what I did in the Excel before.
Band 11 band 12. Yeah, give me a sec. It's around 10, the value.
But if you see it, it's 36,000 divided by 16,000. Is this not a
That's the maximum value in that area, in that region.
that's the maximum, and the average is?
The average will be around, give me a sec. I've calculated the values actually around here. So I only took the white pixels that I showed you just now.
Mhm.
We look at here. This one, right? I only took the white pixels because that's the methane emissions that we have confirmed.
Mhm.
This one and this one for band 12 and this one for band 11. So I only took the white pixels value and I made the ratio. And I got the sum values of band 12 and band 11 over here. So
Mhm.
these are the white pixels value. This one
Yep.
and this one. So I got the
Oh.
sum and this is the band ratio.
From the band 12 to band 11. So that's
Yeah.
the other way around, and so it will be 1.4 something.
You want to do band 11 over band 12, right?
Yeah.
All right, it's 1.39, 1.4.
And now this emission you're looking at is it now on water, or is there some construction below?
It's on a construction.
Yeah.
Platform,
So
yeah.
now we have the problem with the signature of the construction.
Mhm.
So the problem is that the construction itself has. So what you see is not the methane, you see the construction at first, because this is brighter than the water around it.
Oh, I'm sorry. It's not on water. It's on ground. This one is on ground.
It's on ground. It's not in offshore. Yeah.
Yeah.
Yeah, but in principle, that's what you should do now. But the problem is, as I said, you cannot distinguish between a methane and whatever is on the ground if you only have two bands, because this relation is not methane; it's mainly the signature of the ground.
Mhm.
The only way to do is if you have another image of the same area and you normalize it, and then you do the ratio again.
Okay, so yeah, we can do that as well. Let's say I have another image and I normalize it.
Mhm.
How does the normalization works, by the way?
Yeah, that's just you do the same ratio and you compare the ratio images.
Oh, as you
That's
said
a
just now,
normal.
we need to compare the brightness, right?
Yeah, or you for normalization you'd have to do a partial atmospheric correction. In fact, you'd have to get rid of the solar position changes and get rid of it's. There is no easy way around for that. It will be really quite a big, quite a procedure to do that. Yeah. So that's why the easier, the one on offshore, I think, is more promising than on land. I think no way. Simply, it's you won't see it because there's just too much land signatures around. Land is too
Because yeah,
variable
you
in this.
take out the land features.
You would need to know the land features beforehand, then it would work. But as long as you don't know them, no way. On the water, you can estimate that there was no feature because it's only sunglint, and then then it could work. Yeah. But if you have a platform on the water, it won't work anymore. So if it was an oil platform with leakage of methane on the platform itself, of course you will get this construction. So if it's away from the oil platform or over water, it might work.
All right.
Yeah. Is this for the moment?
So what you're saying is basically if it was on ground and there was like external buildings and whatnot, then we would have to take another sample image, right, and normalize it and then compare it, right?
Yeah, and if also what you have just been showing is it's 20-meter data. If you have
Yeah.
only one pixel, the problem is that next time the pixel may be shifted just a little bit, and you will have a different signature of the surroundings. So you'd need on the ground you'd need something which is larger than 50 meters in diameter, or maybe 100 meter in diameter to have one always the same signature below. because of the geometry. So you have large pixels. So you need large objects.
And large emissions.
Yeah. Yeah. Otherwise, it's so if it's a big roof might work, or a long beach might work. Yeah. That's
I see.
yeah, but that's just the limitations. So you took a difficult task.
Yeah, it's just a tryout for us by using a Sentinel tool. So if we use Worldview or any other satellites, that's a lot more promising for us to obtain methane emissions, right? We can follow this method.
Worldview is the same spectrally. You don't get more information from Worldview.
Mhm.
It won't be easier. It's just for the spectral bands, it has more or less the same characteristics. It's just higher spatial resolution. Yeah, you could use in Worldview. You could maybe focus on certain objects where you really know what's on the ground, because there it's not that large, the pixel. If you have such objects, then you could try with those. Then you would have to select pixels, picky. And
Is it possible if I know the site is releasing methane, and is it possible for us to pick us up?
two?
Let's say I know a site that actually is releasing methane on that day,
Uh-huh.
and we use Sentinel imagery to detect methane. Is it possible?
If you already know that there was methane, well, yeah, it depends how much methane you have, and again, what the background is. Yeah.
What the surface albedo is, right?
Yeah. Mm-hmm. If you know the surface albedo of the area, then it's possible, yeah. But yeah.
Mm-hmm. By surface albedo, do you mean whether it's homogeneous or whether it's like full of buildings?
Yeah, if it's homogeneous for a certain area, as I said, 100 meters. If you have 30-meter pixels, 20-meter pixels, the rule of thumb is that you need 3 times 3 pixels of the same. So it makes 3 pixels wide. Should be the whole area at least, such that you get one stable pixel in the middle.
Mm-hmm.
So you have three, because the edge pixels will always be affected. And that's one thing. And the other thing is, if you know what the albedo is of this area, then it could work, yeah. Then you can simulate based on this albedo and feed it to Modtran.
Okay, spectral albedo. That's what
Mhm.
it's. Okay. I understand that one.
Would it be inaccurate if we were to assume the albedo to be just homogeneous? Would the values deviate much if it
Okay.
was
So
assumed?
if you know that albedo is a constant,
Yeah.
it wouldn't deviate. So if you know it's a target which has no spectral features, more or less, and we are doing ratios, it would be okay. But if the albedo had a strong spectral signature,
Then it
then
would
yeah,
cause
yeah,
it will cause a lot of changes. Mm-hmm.
mhm.
I see.
Yeah.
Yeah,
So
I
a lot to
think
digest, I guess.
there's a lot going on in my mind right now, so that's why I'm
It's
too quiet.
yeah, we're quite aware of how complicated it is. So yeah. Yeah.
You just can't take one band and look at it. That's not possible. If it's just
Yeah.
We need to
it's
use.
only very little signature,
So your idea is that we need to make use of multiple bands, and if possible, multiple passing
Mhm.
to see the difference, right?
Yeah,
That will be the best case scenario.
yeah.
Hey Daniel, one question is like, do we need to simulate all the factor like CO2, H2O, ozones, or that's going to be fixed in the simulation, just changing the CH4 only? Or we need to consider other like gas?
Crosstalk, you mean? So ozone, they don't have an influence. in these wavelength ranges.
Yeah,
So
but we
it's
know that
really
CO2 and H2O influence on this band. We know that.
it has a little influence there, yeah. Yeah, so one could do a crosstalk simulation, changing the CO2 as well. But it's still CO2 has more impact at 2 microns and not at 2.2. So 2.2 it's weaker than CH4. So
Yeah.
So one can see if it makes a bit, but CO2 is better mixed than CH4. So usually you don't see a variability of CH4 CO2. So that's why it may change your absolute value, your absolute calibration, but relatively it will not have an impact.
How about
Because
water? How about water vapor? Does it have impact?
Not at these wavelength ranges. It's you're looking at. It's not, no, that it's out. It's in the window. So water vapor absorbs different wavelengths. Yep. Okay.
Okay, so since CO2 it doesn't absorb well at 2 nanomicron, right? What about 1.6? Do we need to take carbon CO2 at 1.6 or?
That just we just had looked at this transmittance plot before, and let's usually no 1.6 is also in the middle of the window. So
Yeah.
so
If I'm not wrong, CO2 is pretty weak at the 1.6 microns.
Yeah.
So it's negligible.
CO2 has 1 at 1.3, and then I could just if I'm plotting this again, what I just did before, and share can share again. This one. So if you just showed you this plot, the transmittance plot, isn't it, before? And it's in the CH4. No, here because CO2 is here you see the crosstalk of the other transmittances, and we have 1.6. Here we have a little bit of crosstalk to CO. This is oxygen. CO2 oxygen. It's they're together in the same thing. That's so there are small absorptions here, but both CO2 and oxygen are well distributed, so they shouldn't affect your signatures. So that's 1.6 and 2.3. What you got here is the total. That's the methane in the total. It's not a single line here. The only black line is methane, and the other one is there's a little bit of H2. Yeah, there's a little bit of water vapor as well. Yeah, you're right. I think there's a little bit of water. Where's the water vapor? That's the. So there could be a crosstalk to water vapor at 2.3. Let me see. That's here. I think the upper one is water vapor. Yeah. So that's would even be more sensitive, so-called sensitivity analysis. So you would have the thing to simulate. That's 2.2, and the Sentinel is a little bit higher. I think it's 2.3, isn't it?
Yes.
It's here, so it's outside of this absorption. So I think 2.3 is really clean enough. What you have is remaining absorptions is really the yep. The remaining absorptions is really the methane itself. What you got here? There's a little bit of CO2. Oh, yeah, you're right. A little bit of CO2 starts here again, but it's much less. Should do a CH4 plot against CO2 plot. One could also extract this. If you want to see the crosstalk, let's do this. Extract spectra from the transmittance, and I go to the help because I have to check out which columns to use. Radiance mode, no, transmittance mode. Here it is. And we have total column. This number 3 is. So you always have to read the help here. Number 3 is the water vapor. CO2 is number 4. And CH4 is number 16. Any others? I think these are the critical ones, huh?
Yeah, that's the only ones.
So one can say it that way, extract spectra, and then I just say it cross. So now I can do a plot of that, a quick plot. Oh, no, I attach them first. One is good enough, yeah. Do a quick plot of this cross, of one of these crosses. Now we get it. The third one was the CH4. And this is the wavelength range you're interested in, you see. So in this wavelength range, the CH4 absorption is more than water vapor. It would be better here, but Sentinel, I think, stops here. It won't go that far.
CH4 is the red color, right?
CH4 is the red one, yeah. That's the absorption of CH4. The CO2, that's similar, yeah. It's the same, but as I said, CO2 is not variable. So this won't affect your, normally won't affect your problem or your, and this is CO2 plus plus O2. O2 is also in the green curve. One should maybe, yeah. And the black is the water vapor. It's always almost everywhere, but here it's quite clean from water vapor. One could have a look at the response function, plot response function of Sentinel. Oh, that's quite broad. So it's not only 2.3, so it's coming from 2.1 to 2.3. It's a very broad band. I didn't know that. So it's covering the whole range from here to there. So you have some crosstalk. It's covering from 2.1 to 2.3. So to make it even more complicated, you have to crosstalk to, yep. You see, this is the response function of the 2.3 nanometer band. It's starting at 2.1 nanometer, micrometer, going to 2.3, up to 2.3. So it's 2.1 to 2.3. It's here. Methane is only at the edge. Yeah.
Yeah, but the band 12 area.
Yeah. Yeah, but it's only half of the band is affected. So and water vapor is even stronger. So water vapor is variable. Thought it was better, but as it's such broad, you will also have water vapor crosstalk. So you'd have to correct for the water vapor as well. So you'd have to do an atmospheric correction for water vapor, and this is done. Yeah, could be done in Sentinel, but as I said, you will. This is not a 2 days endeavor. That's a 2 years endeavor to get something out of it without guarantee of success. So that's why you really need the spectrometers, which only have these specific wavelength ranges to get the oxygen, the the CH4, and even that one is interesting. So they say you even use only this little absorption here at 1.6, 1.7. It's at 1.7 or at 1.6. That band is 1. Yeah, it's not in the CH4. Okay. I guess at this point, I could give you as much as I can, but it's yeah, maybe it's not what you expected.
No, it's a lot to let it sink in, so it's taking a bit time for us because we are trying to understand a lot of different things, especially to generate the sensor radiance. It's a good one, although what you said does make sense. It's not feasible for Sentinel-2. We can still use it for us to get the edge sensor radius for other satellites as well, so it's completely fine. You don't have to worry about that. But yeah, so far we do understand everything, I guess. I mean, do you have anything?
Wait, I just wanted your clarification just now. So regarding the spectral signature of the elements, right, at the 2 microns area, the elements kind of intersect, like they have a very strong spectral signature with respect to methane. So in your opinion, there comes the need for atmospheric correction, right?
There
You
will
would have to
be a
do.
need for water vapor atmospheric or correction. Yes, so one would need to correct the water vapor.
In order to eliminate the unwanted.
Yeah, one
All
could
right.
even because water vapor can be corrected in Sentinel. There is a water vapor band to detect water vapor, and then it should be corrected correctly. And then you can get rid of this crosstalk. And what you then would have is, because usually if you take the standard atmospheric correction, it corrects for ground reflectance, but in this ground reflectance you still will have the methane signature, because the atmospheric correction just uses an average methane as of the mid-latitude summer atmosphere for the correction. And so you could do the calibration and the detection afterwards, but the calibration function will be different because you're working on reflectance and not on radiance anymore.
Yeah.
So yeah.
All right. Just wanted your clarification on that.
Do we still need to do atmospheric correction if we are using band 11 around 1.6? Because that's not much of the water vapor interference in there.
Yeah. So if you use a standard value of water vapor, then it doesn't help, because then everything is corrected the same and you will still have the variability. So you can use the same 2 core from Sentinel, and this will remove the water vapor based on the image.
So for band 12, it's recommended to do atmospheric correction, but for band 11, it's not really.
Yeah.
All right, sure.
Okay. So then I guess we're
I think that wraps things up.
I think that summarizes everything so far. Any more questions from anyone? Hafizi, Najwa?
Well,
Hoa?
Thank you. Yeah, good.
Okay, then.
Thank you so much for tuning in. Yeah, it was a very good session.
Yeah.
And have a good evening.
We really
Thank you.
appreciate it. Yeah.
So we'll get back to you.
Bye for now.
Yeah, goodbye.
Yeah.
Cheers.
Thank you very much. Sorry. Regarding the recording.
Yep, I will have to send you a link, I think, after the recording is stored. Yeah.
Okay then. All right.
Thank you.
Okay. Thank you very much. Have a good day.
Goodbye.